All right, let's dive right in. We're talking about fermentation. Now, I know it's an ancient process, but today, perfecting it is a super high-stakes game. We are on the hunt for what you could call a billion-dollar recipe. You know, it all starts small. Maybe with something like a single drop in a petri dish. And this tiny thing could be a new antibiotic, a biofuel, a critical ingredient for our food. But the question is, how do you take this little microscopic win and scale it up into an industrial process that's actually efficient and profitable? Well, that is the billion-dollar challenge we're going to unpack.
So that really gets us to the heart of it, doesn't it? How do you find that perfect recipe? How do you tweak every single variable? We're talking temperature, nutrients, pH, you name it, to get the absolute best result you possibly can. It's like a puzzle with an almost infinite number of combinations.
And believe me, the stakes could not be higher. If you get this right, you're talking about more effective medicines, cheaper sustainable fuels, and way more efficient food production. The ultimate goal? It's actually pretty simple. Maximize the yield. Because when you do that, you maximize both the profit and the good you can do in the world.
Okay, so to solve this massive puzzle, scientists have a whole toolbox of methods. Let's start by opening it up and looking at the first, most classic set of tools they'd reach for.
This is the one that probably makes the most sense to all of us, right? It's called one factor at a time, or OFAT for short. It's totally intuitive, super logical. You want to see what works best, so you just change one thing, and only one thing at a time.
So the process looks kind of like this. You test a bunch of different temperatures, find the best one, and bam, you lock it in. Then you move on to pH levels. Find the best one there, lock that in. Then you do the next variable, and the next, and the next. It's methodical, it's careful, but you might already be spotting a huge problem here.
And there it is, the big flaw. As the source material puts it so well, the biggest weakness of this classic approach is that it completely ignores how all these variables might interact with each other. I mean, what if the best temperature only works at a very specific pH? OFAT is never, ever going to find that magic combination.
So to see those connections, to see how everything works together, we've got to move to the next level of our toolbox, the statistical powerhouses. These are the tools that let you see the whole big picture.
And this is a huge upgrade. Seriously, it's a totally different way of thinking. You're moving from a simple one-step-at-a-time approach to seeing the entire process as this big, interconnected system. These methods are built to answer that key question. What happens if we change a few things at once? They can uncover these hidden relationships that OFAT just sails right past, and that can lead to breakthroughs that would have been totally invisible otherwise.
What's really cool is how these tools can work together like a team. Think about it like this. Plockett-Berman Design is your wide-angle lens. It helps you scan the whole landscape of variables to quickly find the few that are the real heavy hitters. Then, once you've found those key players, you bring in a tool like Response Surface Methodology, or RSM. That's your zoom lens. It lets you get in super close and fine-tune just those crucial factors to find the absolute peak performance.
So the bottom line is, these statistical tools are just way more efficient than the old-school method. They show you those crucial interactions and can even build a mathematical model to predict how the whole process will behave. Now, what's the catch? Well, you've got to have some pretty serious math skills to wield these tools effectively.
So, we just said you need some serious math skills to build a predictive model. But what if you could get the prediction without having to build the model yourself? For that, we need to go to the most advanced tray in our toolbox, the AI revolution.
This is where things start to feel like science fiction. AI methods use just raw, massive computational power to sift through complex, messy, real-world data, and they find optimal solutions that, honestly, might be completely counterintuitive to a human scientist. They find things we might never have even thought to look for.
So first up, you've got artificial neural networks, or ANNs. Think of these less like a calculator and more like a seasoned expert who has seen thousands and thousands of experiments. You just feed them enormous amounts of data, all the successes, all the failures, everything, and they start to develop a kind of intuition. They learn the hidden patterns to predict what's going to happen next, all without a person needing to write out a single formal equation. And then you have genetic algorithms, which is a concept pulled straight from Darwinian evolution. It's so cool. You start with a whole population of random potential solutions. The algorithm tests them, lets the best ones reproduce and mix their traits together, throws in a few random mutations for good measure, and just repeats this process over and over. After a whole bunch of generations, only the fittest, the truly optimal solution, is left standing.
And if you want to see the difference between these approaches in one simple chart, well, here it is. When it comes to handling data, the difference is just staggering. Classic methods, they can handle very little complexity. Statistical methods are in the middle, they can handle a medium amount. But AI tools, man, they thrive on massive, incredibly complex data sets that would just completely break any other approach.
Okay, so we've got this amazing toolbox, and it's full of classic tools, statistical powerhouses, and these super smart AI tools. Which naturally leads to the next big question: how in the world do you choose the right one for the job?
I mean, it's the question we've been building up to, right? After looking at all these incredible techniques, which one should a scientist actually pick up and use? Which tool is the best?
Well, this little summary from the source material gives us the perfect answer, and the answer is there is no single best tool. It all depends on the problem. If your problem is pretty simple, the classic one-factor-at-a-time method is a great place to start. If you really need to understand how different variables are interacting, a statistical method like factorial design is your go-to. And for those incredibly complex, messy, nonlinear problems, that's when you unleash the power of a genetic algorithm.
So the big takeaway here is really clear. The goal isn't to find some single master tool that does everything. It's about understanding the strengths and weaknesses of each one. The real art and science of this whole thing is in correctly diagnosing your problem and then picking the perfect tool for that specific job out of the box.
And that leaves us with one final and pretty fascinating thought. As these AI tools get even smarter, even better at finding these billion-dollar recipes on their own, what does the future role of the human scientist even look like? Maybe, just maybe, their most important job won't be to run the experiments, but to be the one who asks the right questions in the first place.